Okay, everyone. Good afternoon, everyone. Welcome to our session. And in our session, we have two talks. One is from Dr. Chaochao on learning causal representations for generalization in reinforcement learning, and one is from me about causal inference with instrumental variables. And the first talk is Dr. Chaochao, and I would like to take the opportunity to introduce Dr. Chaochao. Chaochao is a PhD student of machine learning group at the University of Cambridge. His main research interest is machine learning, both in theory and in practice, especially involving how to combine advantages of causal inference based on reasoning, reinforcement learning, as well as deep learning, and apply them to real-world problems in various fields, such as computer vision and healthcare. And Dr. Chaochao will give us a talk on learning causal representations for generalization in reinforcement learning. And let's welcome Dr. Chaochao to give us a talk.
Okay, so thanks for the introduction. So hello, everyone. I'm very happy to present our recent work on learning causal representation for generalization in imitation and reinforced learning. And this is the joint work with Miguel and Bernhard. So as we know, I think most people will agree with me that one of the most efficient way to learn the new skill is imitates the expert in the areas. For example, a chimpanzee is learning by imitating the human behaviors. Formally, in imitation learning, we only have access to the dataset of expert demonstration, where each demonstration consists of a sequence of the observation of action pairs, which can draw from the expert policy. So in this work, we consider behavior cloning approaches that reduce the policy learning to supervised learning by training a discriminative model to predict expert action given the observations. So to illustrate, consider behavior cloning to train a neural network to drive a car. So in scenario A, so the model's inputs is the images of the dashboard and the windshield. And in scenario B, the inputs of the models is the same images, but with the dashboard masked out, right? Both models can achieve a very low training loss in the training environment. But when deployed on the testing environment, the model B drives the wheel, because the reason is that the dashboard has an indicator lighter that turns on immediately when the brake is applied. So the model A wrongly learned to apply the brake only when the brake light is on. So even though the brake light is the effect of the braking, the model A can achieve the low training errors by misidentifying it as a current state. So we can explain this using the causal graphic model. So in this case, right, so we have the 5-dimensional, we assume we have the 5-dimensional, the true state. So only the first three, the red nodes, are the windshield, which the true cause of the actions, and the blue nodes are the dashboard. That actually they have no direct influence on the actions. But in the imitation learning settings, we connect the data in the sequential ways. That means there's some hidden confounders between the hidden states. So due to such hidden confounders, they bear the spurious correlations between the blue nodes and the actions. So in this way, the model A can learn the spurious correlations between the non-causal variables to the actions. So if in that way, the learning policy is hard to deploy to the testing environment. So the same issues also take place in the reinforcement learning, right? So the challenges in reinforcement learning is how to learn the policy, representation, dynamics that do not build on the spurious correlation and they generalize beyond the specific training environment, right? So for example, so when learning a driving policy by interacting with the environment in reinforcement learning, and the background scenario might change across the environment. After training, it's found that the learned policy builds on spurious correlation. That is, action depends not only on the car road features, but on the irrelevant background features as well. So this makes the learned policies fair to generalize on same testing environments, right? So I think that different from the imitation learning, there are three kind of different generalizations in reinforcement learning. So here I just give a toy structure for examples. Here the solid arrow denotes invariant mechanisms, and the dashed arrow denotes the variance mechanisms, right? So in this case, because it's easy to see, only S1 and S2 have the influence to the rewards. So in the decision makings, only these two dimensions should be included for the decision makings. So for the representation generalization problems, we try to learn some functions which can extract the true cause S1 and S2 from the rich high dimensional observations XT. In the policy generalizations, we try to learn the invariant policy, that's pi AT given the first two dimension states only, right? For the dynamic generalizations, in most cases, I think it's hard to learn the whole invariant dynamics. So in this case, we can learn the local dynamics. And in this case, here, ST plus 1, 2 given ST1 and S2 is invariant, right? So these are local dimensions. If in this case we can learn the local dynamics, we just can transfer this local component to the new environment without additional training. So a natural idea to solve this is by leveraging multiple environments to first learn which features describe the spurious correlation and which features represent the stable relations, which then we can build invariant policy, representation, or dynamics only based on these stable features. But what kind of features, stable features, inspired by the independent causal mechanisms? Here, I just give a brief introduction what is independent causal mechanism, which it might be unfamiliar with people have the statistical background. So if we give the data points about the temperature and altitudes in some cities, we have two different ways to decompose the joint distributions, right? We can factorize it as PA given T times PT. That means you assume the temperature causes the altitudes. The other way is PT given A times PA. That means assume the altitude causes temperatures, right? Based on our physical knowledge, we know the PT given A is invariant physical mechanism. That's when you try to transfer the model to the new environment. The second way, you can keep the PT given A is invariant. The only thing you want to learn is the PA, the distribution of the altitude in the new city, right? So if we factorize in the first way, so you have to learn both components from the scratch. That is not efficient way to do the transfer learning. So inspired from the physical mechanisms, we know if given the target variables, if we know it's the causal variables of the target, then we can learn independent causal mechanism, which is invariant across the environment, right? So informally, so independent causal mechanism have the two sides aspects meanings. The first side means the one mechanism doesn't change the other mechanisms. On the information side, that means knowing one mechanism doesn't give any information about the other mechanisms. So this is about independent causal mechanisms. So regarding the issues we talked about previously, so what do we have know about imitation and the reinforcement learning, how to solve this problem so far? So in imitation learning, it's straightforward. So many work has already shown that only policy rely only on the true causal expert action can robustly model the mapping from the states to the expert actions. And in reinforcement learning, and it also has been shown that a representation consisting only the causal ancestors of the reward is the minimal sufficient representations for policy learning. So maybe people will ask why here is not a direct cause or causal parents of the word. It's about the causal ancestors. Here I just give 2 examples. So in these 2 examples, we have 2-dimensional states, and action only affects the first dimension of the states, and the second dimension states affect the word. So from this case, we have to remember the goal is to learn the policy. The policy is the current state depends on the current action depends on current state. So our focus is the gray regions. So in these regions, we can observe that given the reward or returns, that's the expectation of a cumulative reward. That's the same thing. So given the returns, we found that the AT is not independent of the XTI for any I, right? So in this case, that means when you want to maximize the return, the expectation of the cumulative reward, so all the dimension of the state is relevant to the actions. That means when you try to learn the policy, you have to include all the dimension of the state. But if we remove the link between the action to the x1 and add the link to the x2, in this case, we still have to consider both dimensions in the decision making, because in this case, given the word function, the action is also dependent on the both dimensions. So if we remove the link between x1 and x2, in this case, we found that this dependence does not hold any more. So in this case, we only need to include the x2 for the decision making. So if furthermore, we add the inference from the action to both dimensions, in this action, we also only consider x2 because given the reward functions, the AT is independent of xt. So another issue in this case, in practical applications, we cannot directly observe the latent state, right? So we only observe the high-dimensional complex observations. That's the nonlinear transformation of the latent state. So both issues has already explored in the literatures, but the problem is that the kind of work cannot provide theoretical guarantees on both identifiability and the generalization guarantees, right? They also do not provide the unifying framework to understand and analyze these different generalization problems. They just separate and learn the different address the different generalization problems in the separate environment. So in this work, we try to look at the different generalization problems in both imitation and reinforced learning from a unified view. So our goal is to learn a causal representations which can induce and invariant predict representation of dynamics. And from the causal perspective, such representations should be the direct cause or ancestors of the target. So in imitation, the target is the action, and in reinforced learning, the target is the reward. So in reinforced learning, we try to learn the ancestors of the reward, and in imitation learning, we just learn the direct cause of the action. Of course, so because we can search for the ancestor in recursive way, because that means we can first find the cause of the target, then find the cause of the target. So we always can do the recursive way. But in the reinforced learning problems, due to the Markov properties, we only need to do the recursive search twice. So that's a very efficient way. So based on these ideas, so we propose the invariant causal representation learning framework, which consists of the 3 phases. In the first phase, we need to identify the latent state from the observations. Then, after that, we need to determine the direct cause of the target among the identified latent state. Finally, we just learn the invariant predictor, whatever is in variant policies, representations, or dynamics. So the key step is phase 1, because phase 2, we can use an existing called discovery algorithm to do that. And phase 2 is just a traditional empirical risk minimization method. We can treat as a supervised learning. It can do very well. So the key step is how to identify the latent state from the rich observations. So this we can apply this framework to imitation learning, right? So here is the imitation learning setup. We consider a family of environments, right? So in these families, except for the actions, all the other part, we allowed them to change across the environment, because we don't allow the action change across the environment, because that's a common setting in imitation learning. So we can think that if we allow the action space also change across the environments, it's impossible to learn some environment policy which you can deploy to the new environment. So the second thing is we only have access to a data set of the expert demonstrations, right? Each demonstration is the sequence of observation action pairs, right? So our goal is to learn a policy which is able to mimic the expert behaviors across all the environments by the empirical risk minimization. So we can treat it as just as a supervised learning. So based on this, we can apply the invariant causal representation framework to the imitation learning. Then that means we first need to identify the latent state from observations. Then we can determine the direct cause of the actions among identified latent state. And finally, we just learn the invariant policy based on the direct cause of the actions. But here I have to emphasize that we assume the observation X contains all the information about states. That means we do not explicitly consider the partially observable MDP settings. So if we have some partial observed images or settings, we can stack all the frames to avoid these issues. So formally, we can propose a general color graph which can cover many scenarios imitation learnings. So where the solid arrows denote the invariant mechanisms and that one with the changing mechanisms, right? So here we have to emphasize we can additionally introduce the node T+1, which are the observation action pairs in the previous step to help identify the latent state by exploiting the Markov structure in the imitation learning setting. This also can apply to the reinforced learning setting, but for the simplicity, we will no longer to include the nodes in the subsequent causal diagrams. So here, the dashed arrows denote the causal relationship, which might change across the environment. And it's worth mentioning that the red edges induce arbitrary dependencies between the latent states, as long as the resulting graph is a DAG, because so we didn't assume the latent state is a conditional independence or independence. We assume there could be arbitrary association exists between these latent states. So from this perspective, it's quite general and flexible assumptions on the imitation learning problems. And so we can read several key conditional independence from this color graph. The first thing, the underlying color graph is the DAG, because this is the common assumption in the color discoveries. And then we can read, given the latent states, the XT is independent of the environment. That means the data generating process PXT given ST is the environment, right? This is also what we use in the invariant physical mechanisms. And the third one is given the parents of the actions, then the action is independent of the environment, right? That's also is default assumptions in the out of distribution generalization problems. So based on these things, it's still not enough to guarantee how to identify the latent state from observation. So we have to introduce the prior over the latent state. So surprisingly, so the assumption over the latent state is quite general. So we just assume the prior over the latent state belong to a general exponential families in such ways, then we can prove that under these two assumptions with the other mined assumptions on the function space, we can identify the latent space from the observational. So the next thing is with the theoretical guarantee, how can we estimate the latent variables from the data, right? So because we can directly use the variational autoencoder, but the direct autoencoders, they assume the latent variables is independent. But in our case, we allowed for arbitrary connections between the latent variables. So we introduce the score matching, which can optimize the VAE loss functions with the non-independent priors. So the good thing is we can join the training both objective functions in. So after we identify the latent space from observations, we just using the traditional causal discovery algorithm to discover the direct cause of the actions, because in the imitation learning, there is in many practical problems, there exists no instantaneous effect between the state variables. So in this case, the most basic, the PC algorithm is enough to discover all the direct cause of the target. So then everything is done, which is using the supervised learning method, using empirical risk minimization, then we can learn the invariant policies. So this is applied framework to the imitation learning. And for the reinforced learning, that's the same thing. So we have the same first step. We identify the latent state from observations. Then in reinforced learning, we need to determine the ancestors of the reward among this latent state, right? So they also have the very similar causal graph and very similar assumptions on the causal graph. The only difference is the target is replaced with the reward function instead of the action functions. So we actually can using the same algorithm, same data processing and the reinforcement algorithm to identify the latent space from the observations. So actually, so the assumption of the graph is also the same. So here is the data generation is the same thing, and also the similar prior distributions over the latent state. So under these two assumptions, we can identify the latent state from the observations in the reinforced learning settings. Then we can follow the same algorithms to determine the ancestors of the targets and learn the invariant policies and representations and the dynamics in the same way, totally the same way. So according to the description in the previous slides, you can see all the generalization problems in reinforced learning and imitation learning, they actually follow the same causal graph or similar causal graph. So they first need to identify the latent space from the observations, then identify the direct cause or the ancestors of the target, and finally just using supervised learning or the empirical risk minimization to learn the invariant policy representations and the dynamics. So the final thing, I just show some basic experiment. So we first empirically verified identifiability of the state in both settings, right? We conduct a series experiment on synthetic data generally according the family MDPs shown in the figures on the left. the details of going through the data generation process is on the right? So we train on the two environments with different soft interventions on the state. To measure the identifiability, we compute the mean correlation coefficients. The two figures shows that the state can be better identified by our approach, even when there exists an instantaneous effect between the latent states. Our method even can work much better. So to give you a better visualization, here we just conduct experiments on color MNIST, which are originally grayscale but artificially colored spuriously with the class labels. So it's evidence to our method have the much better identifiability. We visualize, so you can see the figures on the left corner, on the right corner. So we visualize the generalized images through performing the intervention upon the latent variables, right? In this task, the direct cause of the label is the digit shape. So when we intervention on the digital cause, we only change the shape of the digit. By contrast, when we intervention on the no causal variables colors, so we only change the digit colors. So we also do the verify the algorithms on the benchmarks. We trained on the demonstration from the two environment and test on one test environment as shown. So our method can consistently outperform the benchmark and generate better to the unseen testing environment. So finally, so I just some take-home messages. So in this work, we invest different generalizations in both imitation and reinforcement learning settings from a unified perspective. Then we propose a general framework which can identify the latent space with theoretical guarantees and on both identifiability and generalizability. And also we propose a general causal graph which can cover the many scenarios in imitation and reinforcement learning settings. So I think I finished my talk. Any questions?
Thanks. Great talk from Dr. Chaochao Lu. Any question from the audience? Okay. Maybe I have two questions. Yeah, thanks. And if I understand right, I think the proposed algorithm requires the assumption that all variables are observed, right? I mean,
yes. So I think in reinforcement learning, so you can think in the partially observed MDP settings, right? So we only observe the high dimensional observations in some trajectories. So the goal is to identify the latent state from the high dimensional observations. That's the key step of this framework.
Okay. Yeah, I mean, is there any way or any suggestion to extend the proposed algorithm to the the reinforcement learning with only partial observed or some variable are unobserved?
Yeah, so I think so in our experience, so we think even in the partially observed settings, because we can use in the recurrent neural networks to accumulate all the past informations, right? To treat it as a summary of the past informations. So we just stack all the past frames and treat it as the observed state to learn the latent state. So I think that's the most efficient way so far in reinforcement learning. So I think the traditional method like belief state, something like that, it's very difficult to work in the high dimensional space. So I think currently most people just using recurrent or something similar to do the partially observable POM-DP problems.
Okay, thanks. Here we have a question from the audience, from Min Zhou. He said, I wonder, can we know what is the physical meaning of the learned latent variable as? Can you see the question?
Yes, I can see the question. So yeah, that's a good question. So the current only way we can do that is just visualize the latent space, right? When you learn the latent variables, you can do the intervention on the latent space. Then you can generate the observations from the learned mechanisms, right? Like for examples. So in this case, we have two kinds of latent state. One is the shape, the other one is the color. So when you do the intervention on the shape, it's only changing the shape of the digit. So that's the kind of the most popular way to visualize and verify the identifiability of the state you learned.
Okay, we have another question from the audience. Can you see the question from the Jasmine?
Yeah. So if y is caused by sin x plus sin x.
Yeah, the question is if y is caused by sin x plus tan like x t minus 1 x t minus 2.
Yeah, so I think that's so I think in reinforced learning setting we have the Markov properties. So the current state is only whatever the actions or rewards is only directly influenced by the previous state. So if you have the multiple step plus time, you can, like I said, you can using the recurrent network just accumulate all the informations and treat it as the previous state. So you can do the same thing.
Okay, great. Because of the time limiting and if you have any more question, I think we can use the the chat bar in the Zoom to communication with the Dr. Chaochao Lu. And thanks again for the next talk and from the Dr. Chaochao Lu.